All right. So quick introductions to our panel. We have David Battle from here in Sydney from Mission Systems, who has a long background with all things autonomous. Raghav Khanna, he helped me pronounce it. I probably butchered it, but from ETH Zurich. Ian Chen from Open Robotics, Open Source Robotics Foundation, the folks that develop and maintain the core of ROS and specifically Ian's work in Gazebo. Matthew Dunboban from Brisbane, from Queensland University, who's he's between sea cruises right now, so it's he may take some time ashore. And Andrea Munafo from the UK, from the Oceanographic Center, the National Oceanographic Center in Southampton. So we're going to go in alphabetical order. We're going to do roughly 5 to 10 minutes each to kind of tell you about some of the work that their groups have been doing, and then we'll collect from there. So, David?
First of all, thanks to Brian for inviting us back. I was a judge in 2014 when I worked for the Department of Defence in Australia. Dug this shirt out, which I cherish and occasionally paint the house with. Since then, however, David Johnson from the Centre for Field Robotics, who is a long-time collaborator of mine, and I, with a mixture of maybe bravery and stupidity, threw in our cushy jobs and decided to do a robotics startup in Australia. So that's Mission Systems there. And we're, obviously a small company and we don't have our own platform. So simulation is quite crucial to us in developing things like customized behaviors and whatnot. So the theme of the presentation this morning really is encapsulated in those first two words, physics-based maritime simulation. So it's really all about getting that simulation as close to reality as possible. I'm an acoustician with a bit of optics. Dave Johnson is a radar guy, so we've got most of the spectrum covered there. Okay, so I haven't got a lot of time, so a sprint down memory lane for me. I learnt maritime robotics on ships, bobbing around in the ocean, in between trying desperately not to throw up, okay? I worked at the time at the Centre for Ocean Engineering at MIT with very fine people like Henrik Schmidt, John Leonard, and Mike Benjamin, who was here in the audience this morning, an old shipmate. So in a particular trial in 2006, which was part of the PlusNet experiment, which I think was funded by Dr. Curtin, who's also here, simulation really rose in priority for us. So being in Boston at MIT, really our choices for testing underwater vehicles were fairly limited due to funding constraints and whatnot. We did have the Charles River, but anyone who knows the Charles River knows why it's a good idea not to operate underwater vehicles in the Charles River. So I embarked on a lot of simulation before the Monterey Bay 2006 experiment, which involved AUVs, multiple surface platforms, towed arrays, and all sorts of technology. And this has all been done in VRML, which looks great, and it's good for visualization. But really, I have to say that it's a bit of a facade, okay? There was a fairly low level of integration in the simulations that we were doing. We were using Moose at the time. The dynamics for the underwater vehicles was computed in Moose. The dynamics for the towed array was done separately in a MATLAB script that was supplied by really smart guys from Vehicle Control Technologies in Virginia. The acoustics, which was done by people like Henrik and myself, was done in clunky Fortran code that was plugged in sideways into the whole thing. And so basically there was a fairly low level of integration. So moving forward to today, and it is an entirely different situation. We have fantastic free software that is available just by virtue of downloading it, okay? And we have these other fabulous developments, GPUs, driven by gamers. They're pushing harder for cheap teraflops. So you can do now in real time what used to be done offline. There are also a collection of very fine libraries like the Bullet Physics Library, OpenCV for machine vision, NVIDIA Optics, Blender, mature middleware such as ROS, Moose, And that little robot Morsey down the left-hand side there is really what I'm going to focus on. It's the modular open robot simulator engine, which is a project out of France. There are the main people responsible for it there. This information is really just copied off the Morse website, so you can read that at your leisure. It's very heavily Python-oriented, okay, which is great. Python's a very flexible, powerful language. But out of the box, if you have a look at the set of default robots that are available, you're looking around there and you're seeing, maybe some quadcopters and ground vehicles. Not really that many maritime vehicles. There is a submarine there, and to my horror, when I first looked at Morse, one of the things people were doing was switching off gravity. Okay, saying we're just bobbing around with neutral buoyancy. What do we need gravity for? We switch that off. Don't do that, because gravity is very important, it turns out. Okay, so when you get into Morse and customize it, as we have over the last 6 months, you can really make things realistic. So this is a little bit of a simulation of Bluefin 21, and okay, it's nice to look at, it's a bit of eye candy, but it's actually a very sophisticated simulation of that vehicle. With all of the instruments instantiated, INS, IMU, forward-looking sonar. It even has a GPU-accelerated side-scan model which generates about 1 million rays per ping at 50 hertz. And I'll say a little bit more about that later. The Ocean module is a procedural GLSL texture which can be arranged to have the spectrum corresponding to virtually any sea state. So a very sophisticated simulation. Some of the other vehicles we've been working on, down the lower left there, you've got the Hydromea Vertex from those crazy guys in Hydromea in EPFL Switzerland, Alex Barr and Felix Schiller. So we're helping them with some trajectory generation for that vehicle. It's got 5 thrusters, tiny vehicle, only 70 centimetres long. Then you have the deep ray vehicle. If you're familiar with the Scripps 6-metre flying wing glider, this is kind of an Australian knockoff, which I started when I was still working for Defence. It's designed, though, to go much faster than the Scripps vehicle, and it's rated to 1,500 metres. Then you have a generic rib there, which can be driven autonomously. It's got an articulated outboard with the force vector being applied through the propeller. And all of these vehicles really use a distributed buoyancy model, which we've perfected in Mission Systems. So essentially, on another layer of the 3D design, you just orient these spheres to represent roughly the distribution of buoyancy and mass, and you have very realistic surface movements for the vehicle, which is crucial if you are interested in things like deployment recovery. Okay, so switching off gravity, no, don't do that. Use simulated buoyancy instead. So this is roughly how Morse works. The Blender game engine gives you the hooks to get in and run this loop. So there is a main which does some system level stuff, and then you get time slices essentially for each of the sensors and actuators. And I've got a little bit of example code there in Python. So essentially on the left-hand side you have the actual simulation going on, and the great thing about this is it's pretty much middleware agnostic. So on the right-hand side you can put whatever middleware you like. It supports sockets, ROS, YARP, PocoLibs, which I hadn't heard of, Moose of course, HLA, and a text mode. Essentially, one side communicates with the other by just sending data through local data maps. So it's kind of a decoupled architecture, and all you really need to implement a middleware is the bindings. So thanks go to Sard at MIT for the absolutely fabulous work that he did on PyMoose, and of course there's PyROS and all kinds of other bindings. So just quickly to look at how you would implement a dynamic simulation, again looking at the glider. So we have the force diagram there, so constant velocity, all of those forces are balanced, okay? In this case, the parameters, the manoeuvring parameters, if you like, came from CFD that was done at the Australian Maritime College by Max Haas, and they were fed into the Python code. So the nonlinear drags and lifts are calculated in real time for a given angle of attack, and then you essentially just stick those values into vectors. And in the Blender game engine, it's simply a case of apply force, apply torque. It's a very simple API. And when you run the simulation, that glider just flies like a glider. And the motion is extremely realistic. We've also implemented things like variable buoyancy trim tanks, and it's really a very sophisticated model. Lastly, in the way of sensor simulation, something we're doing for the Australian Navy to help with, perhaps as a training tool for mine countermeasures, is a tool that is a GPU accelerated sonar simulator. So on the left-hand side there you have the simulated virtual Bluefin 21 with a virtual side scan sonar, and it's running along the bottom in a constant altitude mode. And on the right-hand side there is basically the side scan data that's being spat out in real time. So as I said, about a million rays per ping at 50 hertz there. And all of the beam pattern effects and shadowing is done in real time in optics. And we've shown these images, to people who've spent their lives looking at side scan, and they say, that's looking pretty close to the real thing. So that project came out of a collaboration that I started with Sydney University, actually with Dave Johnson as it happens, and we're going to license that technology back from the university. Okay, so in conclusion, where I think all of this is headed is in more and more realism in simulations. So as we get more computing power, mostly GPU enabled, we're going to be able to get closer to reality, okay? So systems like Morse achieve this very high level of integration now. So you've got the physics engine. We don't yet have the CFD in real time in the simulation, but maybe, who knows, 20 or 30 years time, you can design your vehicle, plonk it in the virtual ocean, and everything will work. But until then, we're doing CFD offline and writing the algorithms to run. So thanks very much.
So when I was creating my simulator for the RobotX challenge, one of the difficulties I had was getting the mesh of the WAM-V model and then determining the volume of displaced water on an uneven water surface. David Battle, you seem to have a model of doing this. How do you go about determining the amount of displaced volume of water on an uneven ocean surface? And is that open source software?
Yeah, okay. So the model we have is pretty flexible, and it's just a little Python class that it looks at your mesh model, and it looks at the hidden layer with the distribution of spheres, and essentially you can set the trim of the vehicle, okay, to any height, but essentially those spheres just represent empty volumes and correspond to buoyancy force. So you play with a little bit, so you distribute the spheres where the buoyancy should be, and really that it just works. There's nothing, no configuration beyond that. And as for that being open source, I think we're thinking along the lines of maybe contributing that back into the Morse code base, because Morse, out of the box, as I said, at the moment is a little weak in Maritime, but I think we can fix that pretty quickly. I think we'll probably end up contributing that to the code base. Yeah.
Cool. Yeah, that would be valuable. I found as like when I do the simulator, I'm more on the graphics side. So when I got to the physics representation, that was the difficult part for me. Yeah, and especially the. Did you find that? Did you use the Bullet physics library in your presentation? Did you find that the dampening forces, the linear and angular forces, were they realistic in water scenarios, or did you have to create your own kind of dampening?
That's a really good question. So the Bullet integration into the Blender game engine is fairly complete, and you have sliders, and you can set the linear and angular damping. So if it doesn't look right, you fiddle with the slider and make it look right. If you want to be more accurate than that, then you really need to code the damping forces in Python. So there are a couple of options there. You can switch off the default damping and add the damping in the form of forces in your Python. So there are two options.
Okay.
And the environment, wind, some, simple wave fields, and then it sounds like the acoustic piece is also going to be of increasing importance in the competition. And again, these are different disparate communities. Like when I talk to the acousticians, I don't mean any harm here, but unless we have the full bathymetry to the centimeter level and we're doing the Henrik, full-on computational model, it's just not worth doing. But I think for our community, there might be some simple models that would run in real time that we could integrate into these tools. It sounds like you may have already done that.
Well, yeah. So in the acoustics, there's the low frequency stuff, which is hard. I would say is a little bit harder, and the high frequency stuff is much easier. That's the sort of ray tracing stuff that we're looking at. So
yeah, the layman can understand. Yeah, straight rays. Yeah, somewhat straight. Yeah. Yeah.
I'd just like to add that I think in a perfect world you would have some kind of system ID capability along with your simulator. That's certainly something that we would implement down the track. And I had a chat with Mike about this last night. Actually, the V&V is a harder one. Particularly when it comes to autonomous behaviours. How do you do V&V? Perhaps the kind of simulation that we've talked about this morning is not the tool for that. I think V&V may require a different tool set.
So I guess my question to the panel is, do you think there is any utility at all in trying to get to the point where if it works in simulation, we know it'll, I came from the University of Missouri, and if the University of Missouri had a team, they're not going to go to the ocean. Could they develop it completely in simulation and then have any success at the actual competition in Hawaii?
I was speaking to Mike Benjamin last night, and we were thinking back to some famous statements that I heard when I started to do simulation at MIT. Somebody said, the thing about simulation is you're doomed to succeed. And actually, we found out... Rod Brooks said that? Okay. I actually thought that was John, but anyway. So we found out pretty quickly that that's not the case. The better your simulation becomes, the more you start to fail. Okay, your simulations fail, and they start to fail for reasons you didn't think of. And immediately that happens, you're saving money right there. Okay. The second quote is from Henrik Schmidt. Okay, and I think he was famous for saying that for every hour in the water that he spent what was it, 100? 1,000 in simulation. Okay, so if that's what Henrik says, that's good enough for me.
Yeah. Yes, I agree. All right. Well, the timer says 0. Let's thank our panelists. Thank you all for your time. And thank you, Musa, for being online, and it's bedtime there, so appreciate it.